Oh my gosh, you came back. Thanks so much. Here's the 3-6 day 2 notes. Write the simplest polynomial function with zeros, -2, 12, and 5. So remember the zeros are like when we solved each part, these are our answers. So if it was x equals -2 for our final answer, that means when it was in parentheses, it would have said x plus 2. For the 0 of 12, you would have written that as x minus 12 in factored form, and then 5 would be x minus 5. So they're saying this is what our final factored equation looked like before we solved it. Now they want to know what the original polynomial would be. So we just need to multiply these. You can multiply them in any order. Let's just say we FOIL these first two. Now remember, when you're factoring and you end up with something like x plus 2 and x minus 12, the first term was always x squared. The middle term would be when you add them together, which would be -10x. And then the last term would be when you multiply them. 2 times -12 would be -24. So if you can kind of remember that, you'll save a step. But if you can't remember that, that's fine. Just FOIL it and you'll get it. And it's not saving much time anyway. So x squared minus 12x plus 2x minus 24, and then you just combine your middle terms. So we have x squared minus 10x minus 24, which is what we just said earlier, I believe. And then we have the x minus 5 that we need to multiply in, and then we'll be done. So let me scoot down here. So let's get them all with the x first. We're just going to be bumping everything up 1x. So that would be x to the third minus 10x to the second minus 24x to the first. And now we'll get them all with that -5. So -5x squared. I'm going to put that with my other x squareds. We'll have positive 50x. And -5 times -24 is positive 120. So if we combine our like terms, we have x to the third power, -15x to the second power, 26x plus 120 equals 0. This would have been our simplest polynomial function there. All right. So again, figure out the zeros, multiply them, and you're done. Combine your like terms too. Also, if there are 3 zeros here, you're going to want to make sure that you at least have x to the third power, because remember the degree is your number of zeros. Write the simplest polynomial with zeros 6, 0 double root, and 23. Okay, so the -6 would be written as x plus 6. Now when x equals 0, remember that just means it's just x. But this says double root, which means it should be x squared. Right? So it's kind of talking about our multiplicity there. So there's going to be x squared on the outside because of that double root. And then we also have the 23. So x minus 23. If I was doing this, I would probably FOIL first and then multiply by the x squared at the end, but it doesn't matter the order. So x times x is x squared, x times -23 is -23x. We have positive 6x, and then 6 times -23. 6 times 20 is 120, 6 times 3 is 18, so it'd be 138 minus 138. All right, we can still combine our like terms here. -23x plus 6x would be -17x. And then we're going to multiply this by the x squared. So it's just putting 2 more x's on everything. So x to the fourth minus 17x to the third minus 138x to the second equals 0. So it's to the 4th degree, so there should have been 4 zeros. Well, -6, 0's in there twice, and then 23. Those would be our 4 zeros. Great. Now we're going to get into some complex stuff, irrational root theorem. If you have a square root that is a 0, it can also be the negative root of that. So if they're telling us the square root of 3 is a solution, that means also negative root 3 would be a solution. So if they're saying negative root 5 is a solution, that means positive root 5 is a solution. They come in pairs. Just the same thing with complex numbers, or the imaginary numbers, the i's. So if you have 4 minus 6i as a solution, that means its conjugate, 4 plus 6i, would also be a solution. So that's where it gets a little tougher. 5i and negative 5i. So the roots and the complex numbers, they have a pair of zeros with them. So positive and negative. So write the simplest polynomial function with zeros, 3 and 2i. So they're trying to trick you. That looks like there's just 2 zeros. But don't forget, if 2i is a 0, that means negative 2i is also a 0. So we would have x minus 3. We'd have x minus 2i, and then we'd have x minus negative 2i, which would turn to x plus 2i. Now the nice thing about these kind of things is you're going to have that difference of squares shortcut that you can do a lot of times. Like if you're FOILing x plus 2i and x minus 2i, that's your difference of squares, where you square the first term, x squared, you make it a minus, you square the second term. 2i times 2i would be 4i squared. Now, you can never leave it as 4i squared, because remember, I squared is negative 1. So negative 4 times negative 1 would be positive 4. So we get x squared plus 4 for all of this. So that part is all handled. Now we just need to bring in this x minus 3 stuff. FOIL this out, and then we're done. X times x squared is x to the third. X times 4 is 4x. Here we'd have negative 3x squared and negative 12. Now the only thing I would change here is to make sure that it's in standard form, which it's not. We need to flip-flop the 4x and the negative 3x squared. So x to the third minus 3x to the second plus 4x minus 12 equals 0. So there's 3 zeros there, which they only showed us 2, but remember, those complex numbers come in a pair. So here we have 0 is a 0 with a multiplicity of 3. So right there, we know we're going to have an x to the third on the outside, and the square root of 2. So we'll have x minus root 2. But don't forget, that comes in a pair. So it would also be negative root 2. So that would be written as x plus root 2. Great. I see a difference of squares. That's going to be the easiest thing to mess with first. Square the first term. X times x is x squared. Put a minus. And square the last term. The square root of 2 times the square root of 2 is just regular 2. So, last thing we have to do is distribute. X to the third times x squared would be x to the fifth. X to the third times negative 2 would be negative 2 x to the third. So this is showing that there are 5 zeros here. Let's look back at the problem. It has the zeros of 3 with a multiplicity of 3. So there's 3 zeros. Square root of 2 is the 4th zero. And negative root of 2 would be that 5th zero. We got 2 more. 1 minus 4i, which means the other 0 would be 1 plus 4i. So this is where it gets a little dicey, because when it's just like a normal number, like if it said the 0 was 1, you just write x minus 1. But here, the 0 is 1 minus 4i. So here's how we're going to write it. X minus 1 minus 4i, and x minus 1 plus 4i. That's just going to be initially. We're going to readjust it here, and I'll show you a quote-unquote shortcut that I like to do with this. So if we distribute that negative in there, it would be x minus 1 plus 4i. If we did the same thing here, it'd be x minus 1 minus 4i. Now there's a property that you learn in Algebra 1 or even before that called the associative property, which is stating that you can associate different parts of the equation when it's an all addition, and it's fine. So it doesn't matter the order that you do it. So if you look, both of them have an x minus 1. So I want you to group that in your head here. So this has x minus 1 plus 4i. This has x minus 1 minus 4i. So it's the same thing, except one has a plus and one has a minus. So we just created a difference of squares here. So you can square the first term, put a minus, and square the last term. 4i times 4i would be 16i squared. Trust me, this will save you a little bit of time. You can multiply the x times all of these, then the negative 1 times all of them, then the 4i times all of them, and it'll work out. But if you can use that associative property and just group together the x minus 1, square it, and then the last term square it, you'll save yourself a little bit of time. So remember, when you square a binomial like this, you could write it twice, FOIL it, or the shortcut was square the first term, multiply them together and double it, so that would be minus 2x, and square the last term, negative 1 squared would be positive. So this is what x minus 1 squared FOILs out to. Then we have this minus 16i squared. I squared is negative 1, so negative 16 times negative 1 would be positive 16. And then we have some like terms that we can combine, the 16 and the 1. So x squared minus 2x plus 17 equals 0. So that is tough. That's about as tough as it's going to get. But I feel like if you can remember that associative property there, that'll save you quite a bit of time. Write the simplest polynomial with zeros 1 plus I and negative 3. So remember, that means 1 minus I will also be a 0. So there's going to be 3 zeros. So our final answer should be x to the third, something. So let's set this up. We'll have x minus 1 plus I. We'll have x minus 1 minus I. And x is negative 3, so that would be x plus 3. Rearrange this formula, and we're done. A lot of work, but all right, let's distribute the negatives here. So that would be x minus 1 minus I, x minus 1 plus I, and the x plus 3. Honestly, we're going to ignore the x plus 3 until later. We're going to work on the stuff on the left here. So if we can associate the x minus 1's together, now we have the difference of squares. We have x minus 1 minus I and x minus 1 plus I. So you square the first term, you put a minus, you square the last term. And then, of course, we'll have to mess with the x plus 3 later. We won't worry about that now. Let's just simplify this the rest of the way. So x minus 1 squared would be x squared minus 2x plus 1. I squared is negative 1, so this is minus negative 1, which is really plus 1. So if we simplify our like terms, x squared minus 2x plus 2. Great, that's what all this simplifies to. X squared minus 2x plus 2. We still need to multiply that by the x plus 3, and then we'll be finished. So let's get them all with an x. The x to the third minus 2x to the second plus 2x. Now let's get them all with a 3. 3x to the second minus 6x plus 6. x cubed plus x squared minus 4x plus 6 equals 0. Woo! Woo! That was tough. We did it though. We did it.